Welcome, welcome everyone. Welcome to the sixth part of our series on analog electronics. We have already studied semiconductors, PN junction, rectifiers, transistors, and transistor configuration. The links to these video tutorials are provided in the description below. Today we are going to look into our sixth topic, operational amplifier, or as it is known famously, op amp. It is a circuit which can perform mathematical operations like addition, subtraction, integration, and differentiation. Owing to these operations, this amplifier is known as the operational amplifier. No course in electronics is complete without studying op amp. We are going to dedicate two full-length tutorials on this particular topic. Now, at the heart of the op amp is a differential amplifier. The construction and working of the differential amplifier is essential to understand the construction and working of the op amp. So, we will first dedicate our time to the differential amplifier. The differential amplifier is something which is shown in the left side of your screen. It has two transistors Q1 and Q2 which are equally matched. That is, they have same characteristics, and the collector resistors RC1 and RC2 are also equal. It is biased by a positive battery VCC and a negative battery minus VEE. It has two input terminals, the bases of the transistor Q1 and Q2, and it has two output terminals, the collectors of the transistors Q1 and Q2. Now let us see how an input is provided to this differential amplifier. The first way is the single-ended input, in which the input is provided to one of the bases of the transistors. That is, in this case, Q1 is receiving the signal and Q2 is grounded. It can be other way around also. That is, Q2 will receive the signal and Q1 will be grounded. Next is the double-ended input, in which both the terminals will receive two different signals. In case of output signal, again, there is a single-ended output in which one of the collector can be utilized to receive the signal and the second collector is grounded, or the alternate configuration can be there. In case of double-ended output, both the terminals can be utilized to receive the output. Here you can see the outputs are out of phase. We will look into it in detail later on in the tutorial. So, depending upon these two different inputs and two different output modes, we can have four different modes of operation for the differential amplifier. The first is the single-ended input, single-ended output. Second is single-ended input, double-ended output. Third, double-ended input, single-ended output. Fourth, double-ended input, double-ended output. Let's look into the first one, single-ended input, single-ended output. So, for single-ended input, single-ended output, the input is provided to one of the terminals, the second terminal is grounded, and if we receive the output from the opposite transistor, we can see that it is amplified and in phase with the input. As the output is not inverted, this kind of operation is called the non-inverting mode of operation. The next case can be that we receive the output from the same transistor. In this case, again it is amplified, but it is out of phase with the input. This kind of an output is called the inverting mode of output. So we have two modes in which if you take the output from the opposite transistor, it is in phase and amplified, that is the non-inverting mode. If you take the output from the same transistor, it is out of phase and it's called inverting. For the second transistor also we can see the same results. So if you give the output to Q2, this is the non-inverting output and this is the inverting output. Let us move on to single-ended input, double-ended output. So we will provide the input to one of the terminals, but we will receive the output from both the terminals. So if you provide the input to Q1 and we receive the output, this is the non-inverting output as we have seen before, and this is the inverting output. But the total output in this case will be the superposition of both the waveforms. Mathematically, it can be expressed as V naught equals to V naught Q1 minus V naught Q2. So the superposed output is this, where you get an amplified output. It can be done with the other terminal also. If you provide it to Q2 terminal, this is the non-inverting output, this is the inverting output, and this is the final output. So in case of a single-ended input, double-ended output, the output is amplified and it is a resultant of the two waveforms that are obtained at the inverting and the non-inverting outputs. So we have two kind of output now, one from two terminals which is called the balanced output, and from one terminal which is called the unbalanced output. Now before we move on to the next two modes of operation, we have to look into two different kind of signals which are applied to a differential amplifier. Let us look into those signals. This is the first type, in which both the signals are in phase. One of them will be applied to Q1 and one of them will be applied to Q2, and both are in phase and their amplitude is also same. So when you have two in phase signals with same amplitude, they are called common mode signals. The other way can be this way, in which both the signals are out of phase and their amplitude is same. That is V1 equals to minus V2, where minus represents that it is out of phase. This kind of signal is called as the differential mode signals. We will use these signals when we will consider double-ended input amplifiers. Let us look into the first kind of that, double-ended input, double-ended output. So we will provide input to both the terminals and we will receive the output from both the terminals. First, we will look into the common mode signal. So we apply one signal to Q1. These are its output waveforms. Then we apply another signal to Q2 and these are its output waveforms. It must be noted that the red and the blue waveform are same. Two colors have been used just for understanding. So as per the voltage equation, you can see that both the waveforms nullify each other and hence the total output is naught. We don't get anything. So it summarizes that the differential amplifier in double-ended input, double-ended output mode rejects the common mode signal. Let us see what it does to the differential mode signal. In the differential mode, again, these are the output for the, we will call it the red wave, and for the blue wave. Here you can see that the superposition is constructive and hence we get this kind of an output waveform. So here the differential mode signal is not only accepted, it is amplified as well. So a double-ended input, double-ended output differential amplifier will reject common mode signal and will accept the differential mode signal. Let us see what a double-ended input, single-ended output differential amplifier does. For the common mode signal, again we do the drill. We see we don't receive any output again. We check with the second output terminal and we do the drill again and we receive no output again. So a double-ended input, single-ended output differential amplifier also rejects the common mode signal. Let us see what it does with the differential mode signal. For the differential mode signal, again we do the drill and we receive the output like this. So it gets amplified, but the amplitude of the output is half that of the previous case. That in case of double-ended input, double-ended output, it was twice this value. Let us do it for the second terminal also. Again we receive the output. So summarizing this, let us see how a differential amplifier works with common mode signals and differential mode signals. First, we will look into the common mode signals. In case of common mode signals, it is rejected, and the gain of an ideal common mode, sorry, the gain for an ideal differential amplifier for common mode signals should be 0, but in practical circuits you receive certain value, and that gain is represented by ACM. In case of differential mode, let us see, the gain is ADM. The common mode signals are rejected, and this action is called as the common mode rejection. Most of the noises and other unwanted signals are common mode signals, and these unwanted signals, when they appear on the input of the differential amplifier, they are virtually eliminated. A differential amplifier should have high differential voltage gain and very low common mode voltage gain. The ratio of these two quantities, that is the differential voltage gain and the common mode voltage gain, is called CMRR, or common mode rejection ratio. In decibel, we can represent it in this format. Ideally, the value of CMRR for any differential amplifier should be infinity, but practically it is about 100 decibels. So this was all about the differential amplifier, which I have said earlier that is in the heart of the operational amplifier. So let us look what an operational amplifier looks like. This is the block diagram of the operational amplifier. As you can see, there are 5 different stages. It is having 2 inputs and 1 output. We will look into the 5 stages in detail. The first stage is the double-ended input and double-ended output differential amplifier, which has a large CMRR, and it produces most of the voltage gain for the op amp. The input impedance is very high for this amplifier. The intermediate stage of the op amp is a double-ended input but a single-ended output differential amplifier. It is driven by the output of the input stage, and it increases the voltage gain and the CMRR of the entire operational amplifier. The third is an ammeter follower, which is just a unity gain amplifier having low output impedance. It basically acts a buffer between the first 2 and the last 2 stages. The first 2 are the input stages and the last 2 are the output stages. The first of the output stages is the level shifter, which is used to shift the DC voltage to 0 volt with respect to ground. Actually, in case of an op amp, it has lot of active elements which even before applying the signal are biased and can produce an output at the output terminal. It is required that when you apply an input to the operational amplifier, the output at that point of time should be 0, and whatever output you receive from the operational amplifier should be due to the signal, and hence it is mandatory that the initial voltages should be brought back to 0. That is done through this level shifter. Last is a class B push-pull power amplifier, which increases the output voltage and the output current because of its low output impedance. So this is basically what an operational amplifier is. Now, if you have been to an electronics lab, you might have come across this IC. This IC is called IC 741 or the op amp IC. Most of the students have problem in identifying the pins of this IC. The trick is to identify the notch. You have to hold the notch to the left of you, and the bottom left pin is 1, and from there on you can continue 1, 2, 3, 4, 5, 6, 7, 8 in the anti-clockwise direction. Let us look into the pinout of this particular IC. It has 8 pins. Pin number 1 is offset null, 2, 3, 4, 5, 6, 7, 8. We will see it in detail. Pin number 6 is the output terminal. You receive the output from here. Pin number 2 is the inverting terminal. If you apply an input to this terminal, the output will be 180-degree out of phase at the output terminal. Pin number 3 is the non-inverting input terminal. The phase of the output is in phase of the signal applied to this terminal. Pin number 7 and pin number 4 provides the DC supply voltages. Pin number 7 is plus VCC and pin number 4 is minus VEE that you have seen in the differential amplifier ago. And lastly, pin number 1 and pin number 5, these are the level shifter pins and they are used to control the DC offsets so that the output is brought to 0. They are therefore called as offset null. That is, they set the voltages back to 0. Pin number 8 is not connected. This is the symbol of the operational amplifier. This will be in much use when we will move on to the next tutorial. Now let us see the characteristics of the operational amplifier which has made it so popular. There are two inputs as we have seen, the inverting and the non-inverting terminals. The input impedance is very high. The op-amp has very small input current and there is no loading of the preceding stage. This will be a very important factor when we will study the concept of virtual ground. It has very low output impedance of about less than 200 ohms and the output voltage is practically independent of the value of load. It has large open loop gain, typically of the order of 10 to the power of 5. We are not going to use this gain. We will be using negative feedback and we will be considering the closed loop gain. It has a voltage gain which remains constant over a wide frequency range. The CMRR is quite large. It rejects most of the common mode signals and it has a very high slew rate, that is, the output changes with changes in the input with a very small lag. That is, the output changes quickly as the input changes. In the next video tutorial, we will be looking into the applications of the op-amp, namely the inverting amplifier, the non-inverting amplifier, summing amplifier, subtractor, integrator, differentiator, comparator. Till then, stay healthy, stay safe. Thank you.